Alright guys, coming back to this problem that I gave you at the end of the last video. I apologize that it was at the end of the last video and I couldn't talk about it at that time. Let's talk about it now. Let's say we decrease volume in this first reaction. Let's say it's at equilibrium. Again, we're doing Le Chatelier's. What's going to happen? Well, pressure overall, all species, is going to increase. So the reaction is going to have to shift in such a way to decrease that pressure. And it's going to do that by shifting to the side with the least amount of gas moles or gas molecules, however you want to think about that. So here, we have a solid, so I'm going to ignore that. We have 6 moles of gas here, and we have no moles of gas over here as well, because it's a liquid. So if this side is the reason why we have a high pressure because of our gas, it's going to shift to the side with the least amount of gas moles, which is technically in that direction or towards the product side. Does that make any sense? If not, make sure you send me a message and I can hopefully help you out a little bit on that. Or ask Mr. Christie, either way. Okay, down here. Let's say we increase volume. Well, that's going to decrease pressure. Okay, well, decreasing pressure means that it's going to try to get back to equilibrium by increasing the amount of gas molecules. So it's now going to shift towards the side with the most moles, or most moles of gas in particular. So we have 2 moles of gas over here, 1 mole of gas over here. Again, it's going to shift to the side with the most moles of gas, so it's going to shift towards the reactants here. Okay, down here, we're decreasing volume again, increasing pressure. It's going to shift towards the side with the least amount of gas moles again. Okay, so we go over here, we have 1 mole of gas here, 3 moles here, so a total of 4 moles of gas. 1 mole of gas here, 3 over here, so a total of 4 moles of gas. It can't shift either way, so unfortunately there is no change. And honestly, the ratio is not going to change here anyways because it's increasing equally across the board. So that's looking at volume changes with Le Chatelier's. Okay, don't forget some of the other changes we could have. If it will let me erase this real quick. Some of the other changes we could have is increasing substances, which again is going to be the same as our concentration, meaning if I add P4, notice it's a solid, it will actually have no effect. So that was a bad one for me to grab, but very common for College Board to do. Solids don't affect equilibrium. Okay, let's say I increase my concentration of Cl2. Well, it's going to shift towards our product side. Let's say I decrease my Cl2. It's going to shift towards reactant side. So same idea as it always has been. Let's say I add helium into this mix. Well, helium doesn't react with anything, so no change. It doesn't affect equilibrium at all. It does affect total pressure, but it affects the total pressure all kind of equally, but it doesn't affect partial pressures. So partial pressures are staying constant at this point in time, so no change is actually seen. So those are some of the Le Chatelier things you could see with gases. Let's look at a College Board problem. This is from 2013, and it's from the practice exam in particular. So we have a 4.32 gram sample of liquid SO2Cl2 placed in a rigid evacuated 1.5 liter reaction vessel. As the container is heated to 400 Kelvin, the sample vaporizes completely and starts to decompose according to the equation above. The decomposition reaction is endothermic. That doesn't mean anything to us right now except for the fact that it gets cold and requires energy. We'll deal with that when we get to thermo in a few chapters. Okay, so let's go through and see what we have to do with this guy. A, if no decomposition occurs, what would be the pressure in ATMs of the SO2Cl2 in the vessel at 400 Kelvin? Okay, well, this should be a very straightforward gas law problem. We have 4.32 grams of SO2Cl2 before it is vaporized, before it's vaporized, and then it vaporizes. So if we say that that is the amount of grams of gas we have before it decomposes, we can now do this problem. Notice 400 is definitely not an STP, so we're going to use ideal gas law of PV equals nRT. So we are working on calculating pressure, so P is what we don't know. Volume is going to be 1.50 liters. N is actually what we're going to need to calculate in just a moment. R, 0.0821, and temperature is 400 Kelvin. So we need N. How do we calculate N? We need moles. So 4.32 grams of SO2Cl2, and we just need our molar mass for this guy. Okay, which has a total molar mass of 134.97 grams, if I just calculated that correctly. And that's going to give us a total mole value of 4.32 divided by 134.97 of 0.0320 moles. So now we plug that in up here, 0.0320, and we calculate out. So 0.0230 times 0.0821 times 400 divided by 1.50. I am getting a pressure of our SO2Cl2 to be 0.701 atms. Okay, so pretty straightforward and easy to do. Okay, when the system has reached equilibrium at 400 Kelvin, the total pressure in the container is 1.62. Calculate the partial pressure in atms of the SO2Cl2, SO2, and Cl2 in the container. So this is a little bit more challenging. What I want you to actually do here, I'm going to come back up here so you can grab the reaction as you need it. Okay, and I want you to come down and try B on your own. I'm going to pause for just a second. You pause as well. See if you can figure this out. It's not hard, a little challenging though. Okay, so let's see if we can work through this together. Hopefully we tried it on our own, we didn't get stuck, and we didn't give up, right? So SO2Cl2 is our reaction. I'm going to rewrite the reaction down here just because it's kind of a pain in the butt to go back and forth like this. SO2 and Cl2. Okay, and that is our total reaction. So when the system has reached equilibrium at 400 Kelvin, total pressure is 1.26 atms. Calculate the partial pressures for all species. Well, it's equilibrium, so what does that mean? That means our wonderful handy-dandy friend, the ice table. So initial pressure for SO2Cl2, we just calculated, is 0.701. We are assuming 0 SO2Cl2 because we only added the SO2Cl2 into the container to begin with. It then decomposed into sulfur dioxide and chlorine. Okay, which means we are losing from this side and adding to our product side. That means we have 0.701 minus X, X, and X. Now, what I want you to stop and think, hopefully we saw this. You were not given a K value anywhere in this problem up to this point in time. And as a matter of fact, if you go down here, you're actually calculating the value of K. So what in the world do? We recognize this information right here. Total pressure in the container is 1.26. What is total pressure? Well, let's go back and think about that. Total pressure is the partial pressures of all the gases in the container. Well, if the total pressure is this at equilibrium, that means these three things added together all equal 1.26. So 0.701 minus X plus X plus X adds up to equal 1.26. Guess what? We now have an equation that we can use to solve for X. Okay, so first and foremost, we have minus X and plus X here. That's going to cancel out, so we're left with 0.701 plus X equals 1.26. We subtract our 0.701 on each side, so 1.26 minus 0.701, and we're left with X equaling 0.559 atms. Now what do we do with that? We take it and plug it back up here. Okay, so if X is 0.559, SO2 is also going to be 0.559 at equilibrium. So is Cl2 because they're both equal to X. Over here we end up with 0.701 minus 0.559, and its equilibrium pressure is going to be 0.142 atms. So there's your equilibrium values. Not too bad, challenging though, because you actually have to think through what's going on here. Okay, let's continue on to the next problem, or the next piece of this problem. Okay, we're asked to write the Kp, so remember our reaction is SO2Cl2 gas going to SO2 gas and Cl2 gas. Okay, so Kp is easy to write. Kp is going to be equal to the pressure of SO2 times the pressure of Cl2, so products over reactants, which is the pressure of SO2Cl2. Please keep in mind you will lose points if you do not write Kp, and if you use brackets at all up here that stands for concentration, you will also lose points. So it does have to be pressured. Now, part 2 of C says to calculate Kp. Well, that just means taking our equilibrium values and plugging it in. Of course, we can use those values because notice up here, whoop, sorry guys, don't know why it's doing that. We are at 400 Kelvin. Jump back down. Guess what temperature we're at? 400 Kelvin. There we go. Sorry, it's being a little spazzy. Okay, so we're going to use those values and plug them directly in. So we end up with 0.559 times 0.559 divided by 0.142. It looks like an 8 that is a 4. So 0.559 times 0.559 divided by 0.142, and we get a Kp value of 2.20. Okay, and that actually technically goes down here, but that's okay. Okay. Notice we're going to skip D for right now. It is asking about temperature changes, which is dealing with thermodynamics, so not quite there yet, and that's okay. In another experiment, the original partial pressures of SO2Cl2, sulfur dioxide, and chlorine are 1 atm each at 400 Kelvin. Predict what happens to the amount of SO2Cl2 in the container as it's going to equilibrium. So basically, if we were to set up our ice table, okay, we would have this idea that ICE, we have 1 atm for each of these. It's technically just 1.0, but I'm writing 1.00. So how do we know which direction it shifts? Okay, we will know what direction it shifts based off of our Q value, which remember Q is calculated the same way as K, so products over our reactants raised to the coefficients. So 1.00 times 1.00 divided by 1.00. Okay, well that's going to give us 1. Well, how does that compare to our K value? Let's go back upstairs and grab our K. K is 2.20 at 400. So what does that mean? It means K is greater than Q. Okay, our Q is too small. So remember, these are both calculated by products over reactants. If Q is too small, it means either A, our reactants are too big, or our products are too big. So we're going to see a shift towards our products, which means we have minus X, and plus X here. So what's actually happening to SO2? SO2 is going to be decreasing because we're creating our product. So amount of SO2 will decrease as this reaction moves towards equilibrium. Okay, so we're going to stop for right now. What I want you to do is work on some of the problems that are up on Canvas. And if you have questions, just shoot me a remind message or a message on Canvas. Thanks, guys.